Okay, so once we go through basic spiking neural network intro and the SNN Toolbox, we're going to go into, I'll tell you more about the upcoming assignment. All right, so I think at the beginning of the course, Dr. Zan kind of went through kind of a little bit of background information about spiking neural networks. There's a lot of neuroscience involved in spiking neural networks. They're really based off of our brain, much more heavily than like the artificial neural networks, and are inspired from them. So just like an artificial neural network, they have what are called neurons and synapses, and they have multiple neurons and multiple synapses or weights connected throughout. But one thing that it doesn't really take into account, like traditional ANNs, are what are called ion channels, which you don't really need to know much about. They're just more biologically related. So what spiking neural networks do is they kind of encode everything into what I kind of think of as biological bits. So in normal digital computing, you have everything being a 0 or a 1 for on and off. And so your brain does something very similar to some extent, but it's a little bit different. So what these biological bits are kind of called are spikes or action potentials. And they're basically the same thing as on and off or 0 or 1, but they're generated in a much different way than, or a little bit different way than the digital like circuits do. So that's all I'm going to kind of go into as far as spiking neural networks today. I'm not going to go into too much more on that other than a spike is, think of it as like a biological bit, a 0 or a 1. So what I mean by spike rates, when I say spike rates throughout this presentation, are that spike rates are basically chains of spikes that happen in a discrete amount of time. So it's like a frequency of how many times does a 0 or a 1 happen within a certain amount of time. So that's what is meant by spike rates. And then we have, so what do spikes really help us do? What's the advantage of using spikes over like floating point values or matrix multiplication or something like that that you see in the normal convolutional neural networks or traditional neural networks? Well, it allows you to have event-based or event-driven computation rather than the continuous, like just compute, and updating and constantly doing multiplications and accumulates and everything. Instead, you only calculate things when you need to. So that's kind of what the advantage is over spiking neural networks and how they're so much more efficient than as far as power, which we'll talk about a little bit later in the course. All right, so a little bit more information about spiking neural networks and their like inspiration. So you'll kind of see this image again probably later in the course because I actually grabbed this from some of Dr. Zan's notes. So this is what a neuron looks like. This you have your input with your soma and everything, like the cell body. And you got all these branches and everything. These are all synapses or dendrites. So, and then you have this long little part of like an arm, I guess you could think of, coming off of the main cell that goes and extends outwards, and that's your axon, which then connects to other neurons later on. So really, I mean, this is just the basic thing. I mean, you can think of ANNs doing this as well, but just not in as like complex way. So anyway, so what's the inspiration behind this and transferring into spiking neural networks? So basically, the inspiration is that you have all these spikes. These neurons spike or produce these little spikes or action potentials. And then they pass those action potentials or that voltage or like 0 or 1 to following neurons. So if this cell creates an action potential or spike, it travels through the neuron and then to another cell somewhere in your brain. So the idea is that this can be also transferred into like a computing model where you have some kind of spike generator or something far on like one side, and it creates these little spikes, these little lines, and they all eventually drive a neuron or a like a node up to a certain voltage. So you're basically adding and adding and adding voltage or potential, and then when it hits a certain threshold, you output a spike. So it basically spikes, it outputs a spike, and then it resets. And you just keep doing this and doing this and doing this. And this is how your brain works, as well as how spiking neural networks work. Is you have some stimulus in the form of spikes as input. You add all their kind of potential up over time, and eventually you hit a threshold or you don't, and then you output spikes. So that's just kind of in the general view of one neuron. Now you can have many neurons in a model, and you have all kinds of different spikes. They're all spiking at different times, and those add up and produce more spikes on the output. So again, not going to go too much into detail about this other than you know what a spike is, and you know that input spikes drive output spikes. Basically, they add up together and produce output spikes. So also, I forgot to mention this beforehand. If you have any questions or anything, feel free to like comment or like open your mic up or just raise your hand or something. But yeah, if you have any questions, feel free to like stop me. Okay. So that's really all you need to know about basic spiking neural networks and what spiking means for this lecture. So now we're going to talk about spiking neural networks toolbox or SNN toolbox. So the motivation behind this is kind of that, as you can already see, neuromorphic computing and spiking neural networks take a lot of neuroscience to kind of develop and kind of create. So that is typically a very hard task for someone like a computer scientist or computer engineer or something to also know neuroscience to develop spiking neural networks from scratch. There are tools and things out there to help you program spiking neural networks, but you still have to know a vast knowledge of things about the cells, the neurons and everything and such. So spiking SNN Toolbox tries to help it be a little bit easier for you to, for a computer scientist to get going with spiking neural networks. So what it's really good at is converting a pre-trained like ANN or CNN or whatever you want to call it to a spiking neural network. It's really easy. It's not hard at all, as you'll see kind of later on in the tutorial or the lecture, but this is much easier than knowing a ton of neuroscience concepts. And the other thing is manual design and training methods is still very new for spiking neural networks. Like people are currently trying to take backprop from like regular old traditional ANNs and try to apply it to spiking neural networks, because we already know plenty about backprop. Why do we need to come up, if we can apply it to SNNs in an efficient way, why should we start from ground zero again with training algorithms and design? So, but there's plenty of different algorithms and stuff that are currently being studied, especially those that require less supervision. SNNs are the kind of, I guess, gold mine is unsupervised learning with spiking neural networks. A lot of people are looking into that right now. But the point is this is new technology. This is like, while SNNs are nothing necessarily new in the form of like theory, they're simulators and everything for years and years and years. The actual hardware and application of them and designing specific ones to accomplish tasks is a relatively new field study. So yeah, manual design of SNNs is hard, mainly because there's a lot of hyperparameters to tune. I mean, you've got the different thresholds, you've got how much should you look at the one synapse over another. There's a ton of different hyperparameters you have to tune by hand to actually accomplish have a working spiking neural network. So, and then the final point that this paper was usually based off of, and conversion is not necessarily new to this paper or to this toolbox. It's been done time and time again to convert a ANN to an SNN, but previous conversion methods didn't have certain layers, and it was a lot more manual of a process to convert. Like I said, the theory was there, but the application or making something more streamlined was not. Excuse me. Okay, so that's kind of the general motivation for why SNN Toolbox was kind of created. All right, so Spiking Neural Network Toolbox, or SNN Toolbox, is a Python package. You can just install it with pip. It's really, to be honest, not really being updated all that much anymore, but it's decently stable. There are some caveats that we will talk about later that you have to kind of be careful of. But for the most part, it's pretty stable as far as the code base. And yeah, so what it kind of aims to do is it tries to map the layers of an ANN to the spiking neural network domain in a one-to-one manner. Excuse me. So it tries to map each singular layer. So if you have a convolutional neural network like LeNet, for example, with 5 layers, then it maps each of those one-to-one in the spiking neural network in the sense that you have 5 layers, 5 spiking layers, that is. So it doesn't try to, there are definitely different approaches to converting spiking neural or artificial neural networks to spiking neural networks that include adding more layers or adding more neurons and groups of neurons and stuff. But for the purpose of like the authors in this toolbox, they just made it simple and are just focusing on doing one-to-one conversion between the layers. So kind of a brief kind of summary of what it does. The spiking neural network conversion toolbox kind of approximates the activations of an ANN that have been trained and then converts those into the spiking domain. So we'll talk about that more. So how does it convert from a ANN to a SNN? So the first thing you have to do is create an ANN. So you have to create something like LeNet-5, VGG, AlexNet, whatever network, MobileNet, whatever. So you have to create that first, and then train it with a certain data set. So you have to do that first. That's the first step. You obviously have to train and get a model that's pre-trained with the weights and activations and everything, and save that model. And then once you do that, you save the model, and then you can start converting. The conversion process is really automated, so you don't have to really worry about it like sitting there and tuning anything. You just basically create a configuration, you pass it in, and it converts it for you. But in general, it's just converting the weights and the activations to kind of a spiking domain to some extent. Okay, so a couple details about the conversion process, which you can either read some of these details or read more about the more granular details of how it actually converts things, is the input images are encoded as spike rates. So what this means is you get an image. Image is made up of however many pixels, and those individual pixels, based on their intensity. So if it's a black and white image, you go from 0 to 255. Those values, 0 to 255, are encoded as spike rates. So you have multiple spikes within a certain amount of time. And then, so after the images are encoded, the activations are also encoded to spike rates, or a certain rate of spiking. And then the biases are converted to some like constant currents and spike rates, and they're clamped to neurons. Again, you don't need to know a lot of this detail. These are just some of those like extra things if you want to read more about it. And then you have some normalization that happens. So a couple advantages of the SNN Toolbox. It's easy and quick conversion, like I kind of said before. You don't have to worry about knowing neuroscience topics and everything. It's less complex and less hyperparameter tuning. You don't have as many things you can like turn the knobs of, or as many settings you can turn the knobs on. And then the accuracies are similar to like state-of-the-art implementations. So training in a LeNet-5 on MNIST is about the same as training an SNN on MNIST, or converting an ANN to an SNN in MNIST. You get similar accuracies there. So you still get lower power. You get lower power than CPU, GPU, TPU, whatever other hardware. Spiking neural networks and neuromorphic hardware tends to do this better with lower power, like magnitudes lower power. Because if you think about a GPU in your computer, either at home or even in your laptop, when you start, if you've ever trained a neural network on it, you know that the fans spin up and it generates a ton of heat. So yeah. Spiking neural networks and neuromorphic hardware really helps keep that power and heat down. And then SNN Toolbox kind of gives you a kind of place to start with neuromorphic and spiking neural networks. That way, like a computer scientist can easily start learning about it without necessarily knowing all the details of how to implement a spiking neural network or all the neuroscience concepts. So it gives you kind of a baseline to start from and test things for accuracy, latency, and power. Okay, so some disadvantages of the SNN Toolbox. So even though this paper specifically kind of went out of their way to create more layers for support, a lot of previous papers were only doing dense layers and that was all they were doing, like just dense layers in a neural network, and that was all that was supported for conversion. This paper tries to implement convolution layers, average pooling, and such, but there are some limitations as to what it can and cannot convert. So the SNN Toolbox actually gives you this table on the right that shows you which layers are supported. So when you're creating your project or your assignment or whatever, you have to kind of refer to this table to make sure that you're using layers that are supported. So if you try to design some neural network that has max pooling in it, you can convert it in the built-in simulator called AnySim, but you can't convert it in something like Brian2 or Loihi or other simulators. They don't have that built in. And some of these are just in general harder to implement or convert to the spiking domain. So some of them just cannot be implemented the way the way they're designed. So so yeah, that's one disadvantage is some layers can't be converted, but that's not just necessarily the toolbox's fault. That's sometimes just the way things are designed. So the toolbox uses what's called rate-based encoding. So it uses spike rates as opposed to individual spikes or spike timing, which we'll talk about more later in the class. And this method of encoding and stuff is just not optimal. It's way more power usage, or it's more power usage, more latency than designing things from scratch, and using other training and encoding methods. Again, this isn't necessarily their problem. It's more of because this is an introduction tool and this is the only way things can kind of be converted in an efficient manner, that this is the reason they used it. So less granular control. Again, this is more of like a beginning tool. There are tons of papers that cite and use this for conversion, but again, you have less granular control over designing your neural networks. It gives you a small set of knobs you can tune, which is both a good thing, but also a bad thing once you start getting going and expand your knowledge. Conversion is a temporary solution. So in the future, while conversion is nice and convenient, it's not really a great solution because it's introducing one more step. Not only do you have to train your ANN and then input it in, you have to then put it in the spiking neural network converter, convert it, and then use it. Like it's not ideal. It's like compiling Python to C and then running your code kind of thing. It's like one intermediary step instead of just running your code directly or running Python directly. And then of course, higher latency than other hardware. Rate-based encoding and conversion methods, again, just aren't ideal necessarily. But I mean, that again comes off as a trade-off, because then you start having all the knobs to turn once you get out of conversion. Okay, so now we're going to kind of go through a demo. But before we do that, I'm going to just ask if there's any questions or anything that I should go over again, maybe. Just going to pause for a little while, kind of let things sink in. I know that was a lot. Yes. Yeah, it'll be posted in the Teams. After we do this lecture, Teams, it's recording now, and so Teams will actually post this recording in the chat where you just did that message, where you asked about it. No time to expiration. No, I don't think it expires. Yes, they will. And if not, we can just we'll always download them and we can post them on Blackboard too if we need to. But other than that, we can figure something out if we need to. Okay, so continuing on, we've got the demo. So the demo is going to consist of converting a model, specifically LeNet, from using TensorFlow and Keras. We're gonna create that model, and then we're gonna convert it with the SNN Toolbox, and then simulate it, simulate the SNN. So basically, this is kind of what we're gonna do. We're gonna go through kind of an installation kind of process. I'll kind of show you briefly show you some of where TensorFlow's documentation is, how you can get started if you're new to TensorFlow. Then I'll show you some of the code that I've created for the ANN creation that you can use for your projects to kind of base your projects off of. And then we'll save the model, move it around maybe a little bit, and then start using the SNN toolbox. I'll show you some of the documentation, how to create a configuration file, and show you how to simulate and see the results. Okay, so we're going to kind of start, and before we start coding or doing any of kind of like technical, I'm going to kind of show you how I've done this, or how I install everything. So if you're not familiar with Conda or Anaconda or Conda Forge or whatever, I've created virtual environments or environment files for all of the different sections of the assignment. So this link for this like GitHub repo is actually going to be available today. It actually already is. But anyway, I've created environment files for each of the different sections of tutorials and stuff that basically have all the dependencies for you ready. So you can just run a simple command. It creates the Python environment for you, and you're off. You're ready. You don't have to worry about installing anything extra. So when you start the projects and you start using SNN Toolbox, I'd highly recommend you probably install some kind of environment management, whether it's Conda Forge with Mini Forge or Anaconda itself. So yeah, you probably need to do this. It just makes your life a whole lot easier. So yeah, I can give more details about how to do Conda Forge and Anaconda later if needed. Okay, so anyway, so each of the different like parts of the tutorials and everything that I've posted are going to have their own environment file, which you just use to create your environment. And once you do that, you can start tinkering around. So the first thing you got to do is create a model using TensorFlow or Keras. Again, just like I showed in the slides, you can use other things. I think Lasagna and Cafe are two of them that you can use to create artificial neural networks, but TensorFlow is kind of the most widely used. I don't think it has support for PyTorch though. So let's see. Oh, it does have PyTorch. So yeah, but in this case, I would advise you just to kind of stay with TensorFlow because that's what I've built off of. Okay, so we're going to start with the ANN model creation. I'm going to kind of show you the code in the browser first, and then how to run it and stuff. So first, we need to create the ANN using TensorFlow. And you can just define TensorFlow. You can just go to TensorFlow's website. Org, I guess. Yeah. So when you go to TensorFlow, you'll kind of land on this website. Again, you don't have to install anything if you use my Conda stuff. TensorFlow is already there in the dependencies list. But yeah, you can go through here if you're not familiar with TensorFlow and kind of learn from scratch how to do something from the most basic kind of 20 lines of code or whatever this is, how to create a neural network. And this one's just a simple dense network. So you have two dense layers classifying MNIST. So this, I mean, if you're not already kind of familiar with TensorFlow, go to TensorFlow's tutorials, maybe try out a couple before you start tinkering around with conversion stuff. Okay. And the other thing that I should mention is I use TensorFlow datasets. So the built-in datasets that TensorFlow has, you can get them here. They have a list of datasets. If you go to tensorflow.org datasets, you can go to their list of datasets and see all the different datasets they have. So for your project, if you're wanting to use different kinds of data, then you can go here and check and see if they have that type of data and import it natively. This is really easy. It's a little bit harder to kind of get it going, but at least you don't have to worry about downloading it and necessarily formatting it as much. It's just you got to learn the syntax of how to code for this API, I guess. So yeah, so TensorFlow datasets, you might want to take a look at those before taking a look at my code. So, okay, back to GitHub. All right, so the GitHub repo has two different folders in it. You got this like welcome page or whatever. You have a tutorials directory. So in here, you have two different directories. You have the model generation directory, which is just for creating your ANNs and saving them. And then you have the SNN Toolbox directory, which is for converting and running the SNNs. So we'll first start with the model generation. So there's a couple notes here that you will probably want to read. Basically, this is just saying that, hey, here's how you run it, as well as here are the little knobs you can dial or turn that are easy to turn. And these are just kind of little flags to turn on and off certain features. Like if you want to remove the model after each run, when you run this code again, it will automatically remove and clean up the old model, so you don't have an old model floating around. Or you can clean up the data if you change something in the code, whatever. And then you can change the number of GPUs you want to run on if you have multiple GPUs. Again, you don't have to, but this is just something you can tune if you have the availability. So then you have a couple other things like the dataset name, how many output classes. This is wrong. I didn't correct it. But yeah, instead of 24, this should be 10. But you have a bunch of other parameters here. You got the batch size that you can train on. You have however many epochs you can have, and then you have your data set like attributes. How much of the data set should be for the training? How much should be for validation? How much should be for testing data? So how much should the splits of the data set be? So training should be 60%, 10% for validation, 30% for testing. So that's basically these are the most important things you can kind of tune in here. Okay, so we're going to start with our LeNet model. So instead of looking at it in GitHub, we're going to change to VSCode. This is a little bit nicer. All right, so same thing, same structure, just VSCode. All right, so all right. So basically, I mean, it looks like a simple Python script. I mean, you import a bunch of packages. Here are the little tunable like parameters that we just saw that you can change at your discretion. And then we get further on. All this does, you don't really need to worry about it. It's just doing some path handling. So it saves certain things to some certain directories and such. Don't need to really worry about this code right here. This is to run on GPUs or not. Again, you don't need to change it if you don't want to. And then there's some helper functions. So all these functions right here really just organize and normalize data. They do some manipulations on the data set after we import them. So it does stuff like the specific function takes all the intensities of the pixels from being integers 0 to 255 and changes them to be floating point values between 0 and 1. 0 being black and 1 being white. So that's really all that block does. This pre-processing just does some things with actually configuring the different data sets. So you've got training, testing, and validation. And then converting to NumPy arrays instead of tensors, just because NumPy is a little bit easier to deal with than tensors and TensorFlow. And then saving the data sets as files, basically. So again, don't need to change the functions. You just might need to use them at some point. And then we actually do the data set stuff. We import the data set here. So we got the 3 different split. We've got a training data set, validation data set, and a test. And then we load it, whatever our data set was, supervised. Again, you can kind of look at, if you don't know what some of these are, then you can look into the documentation for TensorFlow. So TFDS is TensorFlow dataset, so you want to look at the TensorFlow dataset documentation. But yeah, all this is kind of typical information that you need to pass in to create your, format your dataset. And then we pre-process it using the functions, and we save the dataset. And that's it for the kind of dataset part. You don't need to change this callbacks or checkpoints section. You don't need to modify it at all. And then now here's where we actually create our network for our ANN or our LeNet-5. So here's the code that you'll have to change in your assignment, and maybe when you if you choose to use this for your project, is you'll need to change the actual code in here, the layer code. So you can see that from learning about LeNet, you've got 2 convolution layers. Sometimes you can have 3, it really doesn't matter. And then you have 3 dense layers right here, which has 5 layers, so that's why it's called LeNet-5. So this is just a basic LeNet model. So if you wanted to do AlexNet or VGG or whatever, you basically just get rid of this code and write the custom layers here. Okay, so you initialize the model and all the parameters. You just initialize it there, and then you compile the network or the model using the optimizer atom and categorical cross entropy for loss, and then you want to track your accuracy metric. Do a model.summary, and then you actually train the model. So again, here's your training data set, your training labels, and then the number of epochs that you want to train for, the validation to use, and callbacks, and the batch size. And so, yeah, that's it. You train the model, and then if you have one of the flags like train new model is set to false, then it just uses the pre-created model that you have saved. If you don't have a model saved, it'll just dump a file saying file does not exist, kind of thing. And then we just do evaluation. So we actually do the inference to test on a whole separate test data set of what the model does when it sees new data. So that's basically it for the actual coding part. Again, most of the stuff you have to actually change, it lies right here. So just these layers usually. So yeah, let's see how it works. So I'm gonna bring up a terminal. Any questions or comments or anything? Okay, so all right, so we're in a terminal. We have a directory tutorials, just like we already have, and we go into Modelgen. And right now you can see if I do conda, when you get in conda installed and stuff, you have to do conda list or conda, and then that shows you all your dependencies that you have installed. But right now I'm on the wrong conda environment. I'm on the base one, and instead I've created this ANN YAML file, which has all the ANN dependencies in it. So if I do conda env, or let's just do conda activate because I already installed it, ANN. Now I have my ANN loaded, my environment loaded, and if I do conda list again, it's got TensorFlow and everything installed now. All right. So let's go ahead and run this. So run the source. So Python 3 LeNet.py. That's all you need to do to run it. Just Python 3 LeNet.py. And it's going to dump a lot of output, but don't be worried. So right now it's pre-processing the data set, and it's printing out the size of the data set. So all the images in MNIST are 28 by 28 images, and they're grayscale. So that's why you have 28 by 28 by 1, and you have however many 28,000 images or so. And then it started training. So it does a model.summary here. So this actually shows our network. It's got an input of 28 by 28, which is the images. Then it goes through the convolution layers and the pooling layers. And then it classifies in the dense layer, the final dense layer. And then it starts training it. And you can see as it goes, the validation is 94% accuracy, then 96, 97, 97. And finally, it gets to 98. And it saves the model, saves the best model. My code just saves the best model that on the best epoch. So basically, if you have an epoch which actually gets worse, you don't save that model. You save the best one. And then at the end, we do our inference, and it gives you your inference latency and the loss in accuracy, the final one that you saved. So in this case, our LeNet model is 97.79% accurate, classifying MNIST on, I guess, 28,000 images. Okay, so now we have a ANN, and it's saved. So we were in the source directory originally. Now it's saved it in the models directory. So if we go into models, there's our H5 file, which is the saved model, trained model. It's got the weights and the activations that are needed to be for conversion. And then the other thing that SNN Toolbox needs is the data sets. So we save the data sets, and they're in this working directory as these 3 different files. So you got xnorm, xtest, and ytest numpy zipped files. So these are the 3 things you'll need also for the conversion. So we're going to go ahead and copy those over. E-R models. And then we're going to copy them into the SNN Toolbox directory. So that's 1, and then CP working star, then take that to SNN Toolbox directory. All right, so we copied over our data and our model that we trained. So let's take a look at the toolbox now, the code for the toolbox. All right. So again, don't be intimidated by the code. I know it's a lot of code, but it's not that bad. A lot of it you don't even need to change. So you got imports again, and then you've got some like parameters and configuration stuff you can do. So you've got the number of time steps per sample. We'll talk about that in a second. And then we've got a batch size of 32. And then num test sample. So how many samples to test in the data that we gave it, and then how many to batch them by, and then the number of time steps to actually expose each or each sample. So each sample, each image per se, is exposed to the spiking neural network for 128 time steps. So if it's 128 milliseconds, each image gets to be seen by the SNN for 128 milliseconds. And think of this as kind of the latency value of the network. The higher you set this num steps per sample, technically the higher the latency. And then, yeah, so you have batch size, num test samples, and whether or not to convert the model. You don't need to change this because this is just path stuff. This is some cleanup and checking stuff. Copying the ANN to the working directory. And this is what matters right here, this configuration. You're perfectly able to hard code or write this configuration in a text file or whatever by yourself. But I find this easier to do it in the code. So, but you can do whatever you want. I just find this easier. So in this configuration file, we have quite a few different things. We have the working directory path. We have the dataset path. Where's the dataset located? We have the name of the ANN to use to convert. And then we have this run label. And that's just kind of where do you want your logs and stuff to be stored, or the output to be stored inside of the working directory. And then we have some other parameters like evaluate the ANN. So this just tests the ANN on the data that we give it. Parsing. So this parses the ANN. If you set this default, I actually haven't ever tried to set this default to see what happens, but I don't think it would be good. Some normalization, and then simulate the SNN. And then, because you can actually run this conversion toolbox and just convert to the SNN and never evaluate it or test it. You can just convert it and then take that and do something with it. You don't actually have to test it. So that's why that simulate flag is there. So in the simulation, we're going to use the simulator called any, which is their built-in simulator. Duration, again, like I said, is how long each image is seen by the SNN for. And then the number of images to test and the batch size of, so basically if you have a batch size of 32, then 32 images can be seen by the SNN at once, basically. So you don't have to do it sequentially, basically. You're doing multiple images in parallel, so it's a little bit faster to kind of test the SNN. And then Keras backend is TensorFlow. And then from there, we have the output. So again, you don't need to really change this. This is just, at least you don't need to change it in the first assignment, but you get all kinds of different plots and diagrams and such. But yeah, so, and then you can write your config file that this generates and convert the model. And that's it. And then it just tells you where some stuff is. But yeah, so yeah, so let's go ahead and run that. Let's see, get the terminal up. All right, and you can, so we go back a couple directories just to show you where we are. So this is in the GitHub repo. So README tutorials are in the root directory of the GitHub. You go into tutorials, go into SNNTB, then we're in the correct place. So a couple things just to note. The SNN Toolbox looks for certain named files and in certain directories that we've set up already. I wish it was a little bit easier to kind of tell it which files to use and stuff, but it just kind of automatically looks in a directory for certain files. So a couple things we got to do. We have to have this models directory because my code uses the models directory with the model in it. So if we list it, we've got our LeNet-5 model that we created. And then we've got the 3 dataset files. And in order for my code to use this, I have to put it in a data directory. So I'm going to move all the MPZ files into the data directory. If I do ls data, they're all in the data directory. So yeah, I mean, SNN Toolbox just looks for these specific 3 files with called xnorm, npz, xtest, and so on in a certain directory, and that's just how it works. I personally don't like it, but I mean might be the easiest way. Okay, so now we just have to run the toolbox or the code. So you just do Python 3 SNN tb.py. And it takes a second. Oh, and that's because I'm on the ANN Conda environment. So in here, you can see I have this SNN Toolbox environment. So now I need to switch to it. Deactivate. That gets me back to base, and then Conda activate SNN TV. All right, so now I can do it. So Python 3 SNN tb.py. All right. So this is going pretty fast, but after it finishes, I will show you the output. Okay, well, I can show you now. So the first thing it does is it parses and looks at the model that we fed it. So the LeNet-5. So this is what our LeNet-5 had in it. It's got the 2 convolution layers, 3 dense layers. It does some parsing, and at the beginning it does like an evaluation on 100 samples, and it gives you these accuracies, so 97 and 100. And then it kind of does this other parsing thing, or it compiles it, and it gives you a little bit more information. So now it can know, okay, now we have batch sizes of 32, and does that. And then it starts actually converting it and normalizing everything. So, and then it does another evaluation. So it evaluates the model on 100 samples again, and it got 75% accuracy now. Because now it's got a more, the converted like model and parsed model, at least their parsed like ANN model is 75% accurate on 100 samples. Now, if we increased 100 from 100 samples to 1,000 or something, this number would probably be better. And if we trained from epochs and such, it probably would be better in the original ANN. But then after that, it does the actual conversion. It saves the SNN model to this file or this path. So LeNet-5, LeNet-e.h5. And then it starts training, or not training, but classifying the 100 images. So, and batch sizes of, I think, 32 is what it was. So it does batch 1, and it gets 96% accuracy on both the ANN and SNN. And then it does the second batch, and it gets 95 on both, and then it gets 96 on both in the third batch. So then it just gives you some details, tells you the average spike rate was this, and then it says 96.88 on 96 samples. So yeah, that's it. So we actually, it's already been converted. It tested it, and we saw that you get the same accuracy or similar accuracy. This won't always be the case, because when you shuffle your data without using a seed randomly, you'll get different values possibly. So that's it. That's LeNet converted. So it's just run the ANN, create the ANN, save it, move it over, then convert the ANN to an SNN. Done. That's it. It's not that bad. So now that we've kind of gone through the code, any questions? Again, all this will be available starting today. You can start looking over the tutorials at the GitHub repo. And so this will look a little bit less foreign the more you look at it or kind of run it. I would advise maybe starting to run this code as soon as you can, just so that you can start getting an idea. And if you don't know TensorFlow or Python, or you're new to those things, you need to probably start sooner, so you can learn a little bit about those first. Okay, so back to the slideshow real quick. So some layers, okay, so those were the disadvantages. We did the demo. So a couple important considerations about some of the like parameters you can tune. The duration or the num steps per sample flag or like variable, if you start increasing that, you get higher accuracy because you're exposing the image to the network longer, to the SNN longer, but you also introduce more latency. If you lower it, you're going to get lower accuracy, but it also lowers latency. So you've got a trade-off there, and that's actually going to be part of your assignment. Is that we'll see in a second that there's a definite like specific trade-off between accuracy and latency, and then higher batch size. If you run with a higher batch size in terms of the SNN simulation, the RAM, it just explodes. Like you're going to have a ton of RAM usage. So 32, a batch size of 32 is about 10 gigs of RAM on my machine. It uses about 10 gigs of RAM. And if you do like 64, it explodes to 20 gigs. And then if you do 128, it's like 32 gigs. So, or 36 gigs. So try to keep this batch size low, especially if you have a machine that has a lower amount of RAM. The batch size doesn't, you can set it to 16 or even 1 if you want to do. It's just going to take longer to finish the evaluation and simulation. And then the last step to kind of think about when you're using the code is the evaluation step by default performs inference on the ANN and SNN. So when we saw earlier in as it was running, it was classifying or evaluating the ANN as well as SNN at the same time to kind of compare the two as time goes on. So keep that in mind just in case you want to turn off the ANN evaluation or something. And then here's kind of the results of what the SNN toolbox can output. So we were given this 0 in the MNIST handwritten digit dataset. The 0 was encoded as spikes or spike trains, which is over here, right here. And then it's put through the network in this, I guess you could call it a black box for now, or into the converted SNN. And the output is this spike trains of dense 7 dense layer 10. And you can see that the 0, the neuron 0, spikes the most. So that's the one it uses to actually classify. And then below here, you can see the activations and spike rate. So it actually classified 0 correctly. Again, between the beginning spike trains and the ending spike trains are, can't see the trains of spike in Fig 3. So it's really small, and I can actually escape and load the PowerPoint up and zoom in a little bit. So if we really zoom in, you can see that this 0 right here has all the spikes. Like you got a couple small little spikes at 4, 7, 8, and so on. But yeah, most of the spikes are on neuron 0. So yeah, so it did what it was supposed to in this example. So as far as the assignment, thank you, dots on the first column. So it's the bottom row. So you've got 10 neurons. You can't really see 9 because 9 doesn't do anything, but you've got 0 through 9 digits because MNIST is handwritten digits 0 through 9. And you're trying to predict this is a 0 with the network. So the way that the end result knows that it's a 0 is because all the entire row of neuron index 0 there is populated by these spikes. So it's got the most spikes coming out of it. Whereas neuron 2 and neuron 4 just have like 1 or 2 little spikes, which is okay. So we know it's this image is a 0, or the input of the network was a 0 because 0, the ending layer 0, 0th neuron is spiking more than all the others. So, okay, so the assignment that's coming up soon is to create VGG9. So you got 9 layers, CNN, and you're going to classify the CFAR10 dataset. So CFAR10 is a lot trickier or harder to classify with LeNet and other networks. So there isn't a due date for the assignments yet. I would just say if you don't know these things, start as fast as you can, and we'll kind of see how it goes, and how we'll kind of set a due date then, as we kind of see how the class is doing and how much everyone knows. So you'll create VGG9 and you'll classify CFAR10. It's got 10 output images. The images are just a lot more complex than MNIST per se. And then you'll convert the model to an SNN and compare the performance of the SNN and ANN in terms of accuracy. You can't do power and latency really, because you don't really have access to those metrics really, for the SNN at least. And then you'll show an accuracy and latency graph for the different durations of the SNN to kind of show the trade-off between having higher duration and equating to higher accuracy. And then the third assignment will probably be rough. Again, this is a little bit early, is going to be something like analyze the results of the conversion to try to understand them, and maybe a couple other things. Okay, so here's a couple helpful links. I'll distribute this like PowerPoint so y'all can see it on Blackboard or something. And yeah, you got TensorFlow, SNN Toolbox, you got some of so these GitHub repositories specifically have some examples of how to use the SNN Toolbox, some additional ones. So if you want to see more examples other than mine that I give you, you can see them here on the GitHub repos. And then, so that's pretty much it for today. Any questions?